Exam 3 for Physics 201. Which of these is a following is a conservative force? Remember, conservative forces are field forces, and the only one is gravity. The rest of these are contact forces, except for convection, which actually isn't a force at all. It's a method of energy transfer. Massless spring is compressed by 2 centimeters, is now compressed by 4 centimeters. How has potential energy changed? Well, I know that potential energy is 1/2 kx squared. If I double x, that quadruples the potential energy. So C is the right answer. When an increase in speed doubles the kinetic energy, its momentum does what? Okay, so the kinetic energy is 1/2 mv squared. And here I'm doubling the kinetic energy by increasing the speed. That means I'm increasing the speed by a square root of 2, right? Because that causes a double in the increase, or in the kinetic energy. And remember, momentum is mass times velocity. And so if I increase my velocity by a factor of square root of 2, I increase the momentum by the same amount. So it increases, but less than by a factor of 2. When an increase in speed doubles the momentum, its kinetic energy more than doubles, because, well, P is equal to mv. If I double the momentum, that means I've doubled the speed. And if I double the speed, as we've already seen, I quadruple the kinetic energy. If I double this, I get a factor of 4 over here. These 4 blocks are all moving to the right. Which of the forces is doing 0 work? That would only be this one. The angle between the force and the displacement is 90 degrees, and the cosine of 90 is 0. So A is the right answer. There is, by the way, a portion of this force that's doing 0 work, the component that's in the y direction. But overall, the force is doing some work because it also has a force that is parallel, or anti-parallel rather, to the displacement in the opposite direction. 2 trailers have different masses, pulled at the same speed. What is the ratio of their kinetic energies? KEY to KEX. I'm going to write it as a fraction here. It's a half of the mass, which for y is a 2,000. The velocities are the same. So I won't write those out, but those just cancel. The halves cancel. 2,000 over 5 is 4 over 1, or you can write it as 4 to 1. So C is the right answer. Force of 100 newtons acts on a 100 kilogram boulder for 2 seconds. Same force on a 1 kilogram stone for 2 seconds. Which experiences the larger change in momentum? Well, remember, F is delta P over delta T. They experience the same force for the same amount of time, so they have the same momentum. To these statements is true. Energy is a scalar, momentum is a vector, so B is right. Which of these is energy conserved? Only C. In cars and people, these are inelastic collisions, so energy is not conserved. You lose a lot of energy in cars due to deformation of the metal, heat, sound. Same with people colliding. You sort of change the shape of your bodies when you collide. An inelastic collision is one in which only momentum, not energy, is conserved. System of particles has an energy of 0. What can you say about the momentum? Well, the momentum is 0. If the energy is 0, that means that the speed of all the particles is 0. So those particles are not moving at all. Which of these bodies has the largest momentum? Well, P is equal to M times V. So I'm just going to multiply the coefficient. So I'd have a 3, multiply both, 3mv, 4mv, 6mv, and 6mv. Right, that means that 3 and 4 both have the same momentum and the largest. Which of these bodies has the largest energy? Remember, energy is 1/2 mv squared. So it's a little more complicated here because I'm going to square the coefficient of v. So writing 1 through 4 here, I would have 3m. Actually, I'm just going to write the coefficients. So 3, it says 1 times 4 squared, which is 16. 3 times 2 squared, which is 12. And 2 times 3 squared, which is 18. So 4 alone has the highest energy. Okay, I have this particle on a track. I want to know it's traveling at 4 meters per second up here. So up here it has both kinetic energy, I'll call this KE1 and PE1. Here it likewise has KE1 and KE2 and PE2. it's moving and it has potential energy. And then down here it has no potential energy, so it only has Ke, kinetic energy. I'll call this Ke3. And then I also know that at some point up here it comes to a rest, so it only has potential energy, and I'll call that Pe4. So here are the distribution of energies at these particular points, and I know that because of the law of conservation of energy that these have to be equal all the way throughout, so no energy is lost. And I can use that idea to answer these questions. What is the speed of particle 3? Okay, sorry for the interruption, but okay, so in this first part I want to know what is the speed at point B, which is 2 meters high. So I'm going to take the energy that's here and set it equal to the energy that's here. And then I'll solve for the velocity at point B. So part A, I say 1/2 mv1 squared plus mg. I'm going to go and put in this h, 10 meters, equals 1/2 mv1 squared. This is v1 final. This is v1 initial. Plus mg times 2 meters. And actually, I don't need the 1 subscript here. I'm sorry. Sorry, let me change my subscripts here. So this will be a 1, and this will be a 2, representing location 1 and a location 2. Okay, so now my masses all cancel out. I just divide through by m in order to get rid of that. And now I solve for V2. So here, you can do this however you like. I know that over here, this is 1/2 of 16, 1/2 of 4 squared, which is 8, plus 100 equals 1/2 V2 squared plus 20. So it's 108 minus 20, 88 equals 1/2 V2 squared. Multiply both sides by 2. Take the square root of both sides, and V2 then is going to be the square root of 176, which is 13 meters per second. Okay, and then for part B, I'm going to say I want to know the speed at this point. I'm going to set it equal to the energy over here. So for part B, I say mg times 10 meters plus 1/2 mv1 squared is equal to, over here the height is 0, so I just have kinetic energy, 1/2 mv3 squared. And then I solve for V3. So I have, first of all, my masses all cancel. I have 100 plus 8 equals 1/2 V3 squared. So V3, the square root of 216, which is 15 meters per second. And then finally in part C, I want to know the height that it goes to up here. So I'll take the energy here and set it equal to the energy over here. The left-hand side will look the same. The right-hand side now will just have mgh. This is going to be, what did I call this? Location 4, mgh4. Okay, now my masses cancel, and I solve for h. So 100 plus 8 divided by 10, which is equal to h4. That's equal to 11 meters. So that's the right answer. Okay, a spring has a spring constant of 100 newtons per meter. The mass of the block is 2 kilograms. You compress the spring by 10 centimeters in this figure. The spring causes the block to move to the right, and then the block leaves the spring and continues along a frictionless surface. What is the velocity of the block after it leaves the spring? Well, here we're just taking the potential energy, 1/2 kx squared, and setting that equal to the kinetic energy. So over here it has a certain potential energy. And then after it leaves the spring, actually right here, when it leaves the spring, it will only have kinetic energy. So all this potential energy is converted into kinetic energy. And then from this, I can solve for V. Let's see, let's just get rid of those halves. So V is equal to the square root kx squared over m. 100 x is 10 centimeters or 0.1 meters divided by the mass, which is 2. I get 0.7 meters per second. Okay, and that's how fast it's going after it leaves the spring. And then after it leaves the spring, we imagine then that there's a force acting on the block, and the force is dependent upon the position and follows this function. How far does the block travel when acted upon by this force? Okay, so let's just first find the energy. So the total energy that it has is in kinetic energy. That's 1/2 mv squared. That's a half of the mass, which is 2 kilograms, times v, which is 0.7 meters per second, squared. Okay, so my total kinetic energy is 0.7 squared, or 0.5 joules. That's my total energy. That energy is going to get taken away by this force. That force does work on the object, and we can calculate that work. Is going to be the integral of f dx, and this is going to equal 0.5 joules, or rather it's going to equal negative 0.5 joules. That means it's going to take away all that energy. Okay, so I have negative 0.5 joules is the integral from 0 to x of f, which is negative x to the 1/2 dx. Now remember, the integral of ax to the n is equal to ax to the n plus 1 over n plus 1. So this works out to be negative x to the 1/2 plus 1, which is 3/2, divided by 1/2 plus 1, which is also 3/2. And then I evaluate this from 0 to x, and I'm going to be solving for x. So I have negative 0.5 equals negative x to the 3/2, and then I just solve this for x. These negatives go away. 3/2 times 1/2 equals x to the 3/2. 3/4 to the 2/3 power equals x. I get 0.8. 0.8 meters. Okay, an object in this way rest has a mass of 2 kilograms. Force and displacement, how much work is done on the object? Part A, work is equal to force times displacement, or dot displacement, the dot product. That's 3I minus 5J dotted with 2I plus 1J. That's going to be, multiply these terms, that's 6 minus 5 equals 1 joule. Remember, I dot I equals 1, J dot J equals 1, but I dot J and J dot I both equal 0. What is the object's speed at that position? Well, it does this amount of work. So that work is equal to my change in kinetic energy. Pause this for just a second. Okay, so our work is equal to our change in kinetic energy, which is 1/2 mv squared. So that's going to be 1 joule equals 1/2 of our mass. What was our mass over here? 2 kilograms times v squared. So V turns out to be 1 meter per second. Solving that for V. Is the x component of the force doing positive or negative work on the object? Okay, well, let's see, C and D. The question I want to ask here is the force in the same direction as the displacement? And here my x component of the force and the x component of the displacement are both positive, so that would be positive work. Because this 3i term and this 2i term are in the same direction. However, the y component of the force and the y component of the displacement are in opposite directions, so that would be negative work. Two particles collide. What is their final velocity after the final velocity of the second particle? So here I say pi equals pf. I have 1 times 4i minus 1j plus the momentum of this particle, which is 0 conveniently, equals to 1 times negative 3i minus 2j plus 3, I'm going to write this down here, plus 3 times vxi plus vyj. All right, so I'm looking for that v, and now I solve this. So here I have, I bring this over, this part over here, so 4i minus 1j plus 3i plus 2j is equal to 3v final for the second particle. I'm just going to write it in that way and write it as a vector. Okay? So this is 4 plus 3 is 7i plus 1j plus 3vf2 or v2f. And I divide both sides by 3. So I get 7/3 I plus 1/3 j equals v2f. That's my final speed. All right, Alex throws this ball, travels down initially at a velocity equal to negative 6.5, and then it bounces and it travels upward. So this is initial and final. It's traveling upwards 3.5. And I want to know what is the magnitude of the force. So I know that F is equal to dp dt, or delta P over delta T, mvf minus mvi, that's my change in momentum, over my change in time. And we know all these values now, so it's just a matter of plugging them in. That's going to be 0.15, and then I'm going to factor out this m, so I'll have 3.5 minus a negative 6.5 divided by 0.1. You had a homework problem just like this. All right, so that's 1.5 over 0.1, which is 15 newtons. That's the end, I think. Yeah, there's the multiple choice answers.